This is the first section in the chapter Work, Energy and Power from the Further Mechanics 1 book. And this first section, 2.1, is work done. Now, work done is a measure of, well, work done to move an object. Now, that object may move horizontally or vertically. So let's look at a object which is being moved along a surface vertically. Yeah, like this, and we've got the mass of the object m, and we've got some force that's pulling it in that direction. So it means it's either moving at a constant speed or it's accelerating that in that direction. The distance that object is moved. So if I do this arrow here to represent the distance that is moved, well, work done is basically this force, this horizontal force, it's moving in a horizontal direction, multiplied by the distance traveled in that direction. So we're looking at a horizontal movement here, so you've got a horizontal force, a horizontal movement, because that's its direction of motion. So work done, let's write this down, work done equals, we'll just call it F times D. So force times distance, and work done is measured in joules. Now let's say, for example, that that pulling force here wasn't horizontal. Let's say, for example, it was at an angle. So let's do a slightly different diagram here. And let's say that the pulling force was like that, and the angle to the horizontal was theta. And again, we're talking about it moving a distance of d. Well, this time we still need to look at the horizontal component of the pulling force, and in this example, this horizontal component of the pulling force here would be F cos theta. So we're looking at the horizontal component of that pulling force. So in this particular example, work done would equal, well, now the pulling force in the direction of motion. So we'll say that it's either accelerating or moving at a constant speed in that direction, and the pulling force in that direction is F cos theta. So in the first example, that was just F, but it's at an angle here, and that's still times the horizontal distance of movement. Now let's look at an object which is being pulled up horizontally. Yeah. So we've got a mass m here. I suppose I should put a mass m here. So notice on these first examples here, the mass is not included in the calculation, unless, for example, you were using F equals ma to work out F here or here, then you would use the mass. So let's say that something is being raised in a vertical direction. So this time this is moving up either at a constant speed or it may be accelerating upwards. Now this time we will need the weight of the object, which is mg. Okay, and we'll also look at the distance that it's travelled this way. Now this time the work done against gravity needs to overcome this force mg. So it's mg times this distance that it's moved. So now the force, if you were, is actually what needs to oppose mg to get it moving. So it either needs to be equal to that or greater than that. It all depends whether it's accelerating or moving at a constant speed. And this distance it moves up, well, this is just going to be the height that it moves up, or height if you're American. So we use d to represent the distance moved in a direction of motion. So in this case, work done equals mgh. So the mg is like the force that overcomes that, because that's basically the weight that's going down, that's that force there, times by h, the vertical distance moved. So here we can work out work done, whether something's moving in a horizontal direction or a vertical direction. Okay, a box is pulled 7 meters across a horizontal floor by a horizontal force of magnitude 15 newtons. Calculate the work done by the force. So let's do a diagram of this. So here's my box and it's pulled 7 meters. So let me just put this to show that it's moved 7 meters. And it's pulled by a horizontal force of 15 newtons. So we want to work out the work done. So it's basically the force times the distance. We'll just write down work done equals this force times distance. In this case, very easy, 15 times 7. So if I work that out, 15 times 7, and that gives me 105. So it's 105 joules. That's the work done, 105 joules, and we can just use J for joules. A packing case is pulled along a horizontal floor by a horizontal rope. The case moves at a constant speed and there is a constant resistance to motion of R newtons. When the case has moved a distance of 12 meters, the work done is 96 joules. Calculate the magnitude of the resistance. So let's do a diagram and then we'll talk about what important bits of information are in here that we can use. Okay, so we know that it moves a distance of 12 meters. Okay, and it takes 96 joules to do that. It says that it's moving at a constant speed. Now what that means is that the horizontal rope that's pulling it, that force there, is equal to the resistive force of R newtons. Yeah, so because it's moving at a constant speed, you can say that these forces are balanced. So R equals F, F equals R. And we also know that the work done is 96 joules, so we can use that to work out what F is. So let's start by writing down the work done equals force times distance. So in this case the work done is 96 joules. The force F we don't know, but we know the distance is 12 meters. So that means that F is going to be 96 divided by 12, which I believe is 8. 96 divided by 12, yes, 8. So it's a force of 8 newtons that's pulling. So let me just put that here. So this equals 8 newtons. So that equals the resistive force, which is also 8 newtons. So we can write down, there's a couple of ways we could do this. We could either say that just F equals R. Yeah, so we find R is 8 newtons. Or you might say, well, the resultant force equals 0. So you could say that the pulling force minus R equals MA. Yeah, and because it's going at a constant speed, the acceleration is going to be 0. So you can put their constant speed. So you'll end up with the same working. It's just a different way of, or the same answer, a different way of laying out your working. So either way, you'll still end up with R equals 8 newtons. A bricklayer raises a load of bricks. So is that a load of bricks or a load of bricks? Anyway, of total mass 30 kg at a constant speed by attaching a cable to the bricks. Assuming the cable is vertical, calculate the work done when the bricks are raised a distance of 7 meters. Now you'll probably notice in all the questions we've done so far, it's a constant speed. Yeah, which means that the force used to raise something or pull it to one side is going to be equal to the resistive forces. So in this case, the total mass is 30 kg, which means that the force going down is going to be the weight of the bricks, which is 30 g. That's the weight of the bricks. And this cable, well, we're going to get tension in the cable, remember, that's going to be pulling that way. And because it's moving up at a constant speed, so the acceleration equals 0. Or you could say, well, basically that T is going to equal 30 g, because those forces are going to be balanced. Forces are always balanced when things move at a constant speed. So we want to work out the work done. So the pulling force is going to be T, or let's write down our formula first. Work done equals force times distance. Now it says it's raised a distance of 7 meters, so let's do something like this to show that it's gone up 7 meters. So in this case, the work done, well, the force is actually going to be the tension times by the distance, which is 7 meters. Now we know that the tension equals 30 g, yeah, because those forces are balanced. So you could just put T equals 30 g, or if you want to go the whole hog and use F equals ma, you would say, okay, something like the resultant force, which is T minus 30 g, equals ma. 30 times a, the acceleration is 0. You'll still end up with T equals 30 g. So now we've got 7 times by 30 g, which is 210 g. So I suppose you could leave your answer like that, 210 g joules. If I multiply that by 9.8, so 210 times by 9.8, and I'll get 2058 joules. So, or 2058 joules, which you could leave like that, or round to 3 significant figures, and I give you 2060. Package of mass 2 kg is pulled up a constant speed, up a rough plane which is inclined 30 degrees to the horizontal. The coefficient of friction between the package and the surface is 0.35. The package is pulled up 12 meters, upper line greatest slope of the plane, and there's some things to calculate. Now, if you're doing this as one of the first topics you've done in further maths, there's going to be a lot of stuff here that you won't actually start doing until you get to year 2. So I want to put a link below to a couple of my videos which you can watch, which can help you with some of the concepts here. So we've got this mass on the slope, 2 kg, and we're told that it's inclined at 30 degrees to the horizontal. So we're going to put in the weight of this mass, which is 2g, so that always points down. Then we've got this pulling force that's pulling it up the slope. Then we've got this resistive force, which is, we talk about mu r. Again, I'll put a link to the video about mu r. You may not understand what that is. It may be something you've done in physics, and that's going to be 0.35 r. So the r is the normal reaction here, and that's all the forces that are needed on that diagram. So let's start with part A. Part A, the work done against gravity. Now the work done against gravity is going to be the height that this object has moved. Now we're told that it's moved up 12 meters this way. If this is 30 degrees, we can use trigonometry to work out how far up it's gone. Yeah, that's our height in our MGH. Now, simple trigonometry, that height that's been moved up is going to be 12 sine 30. Now sine 30 is a half, so it's moved up 6 meters. So substituting into mgh, so m, the mass is 2, g times by h, which is 6. So we could leave the answer as 12 g joules, or if we multiply the 12 by the 9.8, 12 times 9.8, we get 117.6 joules. So 117.6 joules is the work done against gravity. Right, in part B, we need to find the work done against friction. So remember, work done is force times distance. Now, because this is going up at a constant speed, which basically means that the acceleration equals 0, that means that this pulling force equals this force here. So F equals 0.35 R. So again, I've got a video that talks about this thing here, mu, coefficient of friction. So first thing I'm going to do is to say that this pulling force F equals 0.35 R. Now we also need to work out what R is. R is unknown. Now R is going to be equal to the force going the opposite way to it. Now that's going to be this here. Okay, now we do have this component of a force, but we don't need that in this question. So 30 degrees there. Again, as I said, I've got videos all on this that can help you with that. So this force here, which is actually going to be equal to R, because they're opposite, equal and opposite, is going to be 2g cos 30. So our second equation is going to be also R equals 2g cos 30. So now we're ready to write down what F is. So F equals 0.35 times 2g cos 30. Now we could probably work that out. So 0.35 times 2g cos 30. Okay, and that's 7√3/20g. So let's just write that down as a decimal. It's too fiddly. So that will give me 5.94. 5.94. Okay, it goes on. I'm going to use the exact value in a minute. So work done is going to be this 5.94, the exact value, times by 12. So this bit at the beginning here, the 5.94 is the force, times by the distance. So I'm just going to take my answer, times it by 12, and I get 71.29121124. So that becomes 71.3 to 3 significant figures. So 71.3 joules is the work done against friction. A sledge is pulled 15 meters across a smooth sheet of ice by a force 27 newtons. The force is inclined at 25 degrees to the horizontal. By modeling the sled as a particle, calculate the work done by the force. Okay, so here's our sled. It's smooth, so there is no resistive force. The pulling force is 27 newtons. The distance moved by the sled is 15 meters. And let's get this right. That pulling force is inclined at 25 degrees. I did a horizontal force. So let's change that so that it's inclined at 25 degrees. So 27 newtons. So this angle here is 25 degrees. Now right at the start I showed you how we do questions like this. We're interested in the horizontal part of the force. Okay, that's what we want to find there. So that will give us, if we work that out, so the horizontal part of that force is 27 cos 25. Okay, so simple trigonometry will give us that. So because it's moving a horizontal direction, we only want the horizontal part or the horizontal component of that force, and work done is going to be force times distance. So the force is this 27 cos 25, and we're going to times that by the distance of 15. So let's work that out. 27 cos 25 times by 15, and we get 367.054. So we're going to give our answers to three significant figures. So that would be 367 joules. 367 joules. Okay, you should now be able to do exercise 2A on pages 18 to 19. Again, I will put a link in the description on the other videos that you'll find helpful on doing those problems where you've got a mass on an inclined slope.